Welcome back. Today we're going to talk about electric charges and electric fields. And both of these words, electric, come from the word electron. Electron, as you probably already know, is a particle that is charged negatively and that moves around the nucleus of an atom. All atoms have electrons around them. So because every material is made of atoms, every single object in the world has electrons. But some of them have the possibility of electrons moving easily through them, and some are harder for electrons to move through. So these are divided into two categories: electric insulators and electric conductors. So electric conductors are materials through which electrons can travel easily. An example of one of these materials is metals. Metals can be charged because electrons can travel easily through them. So, metals. And then we have electric insulators. So, insulators are materials in which electrons can't travel easily. It's hard for them to move around. Some examples would be plastic and rubber. So when you have an electric conductor, so electrons can move easily through it, you can do something that is induce a charge into it. So all objects are naturally neutral in charge. They don't have a net positive nor negative charge. But if you put close to it something that has a charge, you can induce a charge in the neutral object. So this is called induction of charge. And it looks something like this. Imagine you have a positively charged object. That means that it has positive charges all over, more positive than negative. And you put it close to, let's say, a very small piece of paper that has positive and negative charges because it's made of atoms, and atoms have protons, which are positive, and electrons, which are negative. So let's say it's neutral in general. But when you put this close, when you bring it close to the piece of paper, what's going to happen is that the charges are going to move. So you have a piece of paper. And what you need to know about charges is that like charges, the same charge repels the same charge, and opposite charges attract. So don't forget that. Like charges repel, and opposite charges attract. So that means negative and positive attract, positive and negative attract, but negative and negative repel, and positive repel. So if you put a lot of positive charges close to the piece of paper, the negative charges in it will feel an attraction because positive attracts negative. So the negative charges will all move to the left to be close to the positive charges, while the positive charges will feel the repulsion from the other positive charges and they will move to the other side, right? So this means that a charge was induced in the piece of paper because it was neutral, but now it's sort of charged because now this part is charged positive and the other part is charged negative. So that's induction of charge. But this induction of charge is temporary. As soon as you take away this positive charge, the charges will realign, and again, it will be neutral. It won't be charged anymore. And something else to remember is that the charges will be conserved. I'm not sure if I drew it correctly, but the same number of charges that there were at the beginning will be there at the end because of a very important law called conservation of charge. What conservation of charge basically means is that no matter if the charge is rearranged, you will always have the same total amount of charge that you did before. So we can use this conservation of charge to do an example. So suppose you have two charged metal objects, so they are conductors. One has a charge of +2, and let's say the other one has a charge of -1, right? And you put them together. Because they are both conductors, the charges can actually jump from one ball to the other. So they will move and rearrange between the two objects. So what happens is that here there was a total charge of 2 minus 1, positive 1. So here there's also going to be a charge of positive 1. But when you put them apart, because these charges will mix, then the charge will divide equally between the two objects. So at the end, we will have, here there's just going to be who knows where, plus 2 and negative 1 between the two. But when you separate them, what you're going to have is that they divided equally. So in order to give plus 1, to have them divided equally, this has to be plus 0.5, and this has to be plus 0.5. So even though there is no longer a negatively charged object and a positively charged object, but two positively charged objects, they do follow the law of conservation of charge, because the total charge at the beginning was plus 1, and the total charge at the end is plus 1. So for this, you need to remember two things: that the total charge always has to add up to the same thing, and that if you put together and then draw apart two objects, the charge will divide half and half. Now let's talk about electric fields. So any charge, either positive or negative, has around it an electric field. An electric field means an area around a charge where other charges will feel a force. So let's say you have a positive charge in space and nothing else, just a positive charge. If you put another positive charge, let's say here, because equal charges repel, this charge is going to feel a force that pushes it away from it. So that charge here will feel this force that pushes it away, and the charge here will also feel a force pushing it away. So this is how we represent an electric field for a positive charge. So basically, we represent it as arrows of the direction in which a positive charge would move if it were placed there. So placed here, it would move in this direction. If a charge were placed here, it would move in that direction, away from the positive charge. If we have a negative charge, it's going to be the opposite. So if we have a negative charge and we place a positive charge, because positive and negative attract, this positive charge will feel a force towards the negative charge. A positive charge over here would feel a force towards this negative charge. So how we represent an electric field for a negative charge is with arrows going towards it, the opposite to a positive charge. So for example, if you have this charge, you place it here and it moves away from the charge, it's this natural movement and it will accelerate the charge, so it'll give it some kinetic energy, some energy of motion. So a charge moving naturally by the electric field it feels will gain kinetic energy, and it has to do no work. So charge moving naturally gains kinetic energy and does no work. But what if instead we wanted to do the opposite? What if we wanted to move this positive charge closer to the positive charge? Or what if even though there's an attraction here, we wanted to move this positive charge away from the negative charge? Then we would have to do work. So to move a charge away from the natural direction requires some work. But because it requires work, it'll give it some energy. The type of energy that charges gain when they move against the natural direction is called electric potential energy. So charge moving opposite from the natural direction will gain electric potential energy, and work has to be done. So basically, whenever a charge moves in an electric field, it will gain energy. Either it gains kinetic energy by moving in the natural direction, or it gains electric potential energy by moving in the opposite direction, but for that to happen, some work has to be done. The same amount of work that was done is equal to the amount of electric potential energy that the charge will gain. And just to give a quick introduction to what we're going to see in the next video, this electric potential energy that it gains is called potential difference, which is also called, and you might have heard it spoken as, voltage. This voltage is defined as the amount of energy the charge acquired over the charge. So if a charge of 2 acquires an energy of 4 over 2, the voltage of the charge would be 2. So we're going to look at that further in the following class. And finally, let's talk about the amount of force that a charge feels when it's placed in an electric field, when it's close to another charge. So charge is actually measured in a unit called Coulomb. Coulomb from the guy who discovered it. So the unit of charge is Coulomb. And we write it as a C, an uppercase C. The charge of an electron is actually 1.6 times 10 to the negative 19 coulombs, and it's negative. If I want to figure out the force, the electric force between two electric charges, maybe between two electrons or groups of electrons, how could I calculate that? So that's called the Coulomb's law. Coulomb's law. Again, just like the unit Coulomb. And Coulomb's law says that the electric force is equal to K times Q1 times Q2 over R squared. So in this equation, K is the electric constant, and it's always equal to 9 times 10 to the 9 newtons meter squared over Coulomb squared. So that's just a constant that you always put into the equation. Then we have Q1 and Q2, which are the charges, and they're given in coulombs. And we have R, which is the distance between the two charges. And it's given in meters. So this is in meters, this is in coulombs, and the constant is in newtons meter squared over Coulomb squared. So when you put everything in, you're going to get a force in newtons, like we always have. Maybe you remember that the equation for gravitational force looks very similar to this. The gravitational force equation is a constant g, the gravitational constant, times a mass 1 times a mass 2 over r squared, the distance between the masses. It's actually the same type of law, it's exactly the same, but with other values. And these two laws are called inverse square laws. So all laws in physics that are proportional to 1 over the distance squared are called inverse square laws because the distance is inverse and squared. But right now we're just going to focus on Coulomb's law, this Coulomb's law. So if the force gives you negative, that means that it's attractive, because that means that one of the charges had to be negative and the other one positive. So negative is attractive. If you get a positive force, it's because either both were positive, and positive times positive is positive, or both were negative, and negative times negative is positive. So when they're the same charge, they repel. So a positive Coulomb's law means a repulsive force. So that's it. Basically, if you're given two charges and the distance between them, you can calculate the size and the direction of the electric force between them.